So now we're starting to talk about, things that are more related to the physical world around us, some real chemistry. So we talked a lot about numbers, accuracy, measurements and stuff. Now we can actually start talking about matter. All right, and so energy is defined as the capacity of matter to do work. Right? So what does that mean? What does energy have the capacity to do work meaning? So work in a physics definition, the work is usually defined as the force times the distance. Right? And we're not here to learn physics, but it's related to when we're talking about energy. Right? And so we think about what is that? That means how much force does it take to move something a specific distance. Right? And this is easy to think about when we think about moving physical objects, right? We can think about the work, we have an actual comparison. Well, if I need to carry, something 5 pounds up the stairs or 100 pounds up the stairs, I'm gonna have to do a lot more work to carry 100 pounds up the stairs. I have to exert a lot more force to do that. And what does that give us? That gives us a unit of energy, right? So work of force is a kilogram. So if I look at the dimensions, right, remember these brackets can mean dimensions. So kilogram, meters per second squared. And a distance is just a distance of meters, for example. Right, so these are going to be our units of energy. And we'll talk a little bit more of that in a second. That's what we're going to define as a joule, what's called a joule. Right, and so we think about moving stuff. That gives us an intuitive description of what work is. But everything in the world around us is pretty much governed by how energy moves. We move usually from high to low energy. Everything in life and in the universe wants to move on the least path of least resistance, right? What's the smallest energy I can reach? That's where I'll be the happiest. And so generally, there's two types of energy that we think of in physics and in chemistry and in pretty much every other natural science. So does anyone know what these two forms of energy are? Stored versus moving energy? Potential and kinetic energy, right? So potential energy, let me not use the same color as the background. Potential is our stored energy, and kinetic is our moving energy, right? This is related to how fast particles are moving. We'll find that that's related to the temperature. In potential energy, this is how much energy is stored. So these can be, a little hard to grasp. Kinetic energy, I think, is a little easier, right? If something's moving, you say that has some energy, right? If that runs into something, there'll be something that happens. Potential energy is usually like how much energy is stored there. That's a little harder to visualize. And so one way we can think about it is if we're lifting a weight above the, here they're using it to put a pylon into the ground. If you lift it up into the air, it has potential energy, right? It has stored energy because as soon as you release whatever's holding that weight in the air, it'll transfer that potential energy into kinetic energy, right? So energy that's stored is called potential energy, and that's ready to be converted to another form of energy. Summer, do you have a question?
So like when the kinetic energy, when that hits the ground and it stops, it would be back at potential energy?
So once it hits the ground, then pretty much it's reached its lowest energy, and it won't really hold any potential energy in the form of gravity, at least in this case, right? Its kinetic energy will have gone to zero, and its potential energy will have gone to zero. But if we think about everything once kind of moved to the lowest energy possible, then that's why it moved in that direction, right? You can think about potential energy as, how can that be converted into another form of energy, which is usually kinetic energy. And then kinetic energy is the energy of movement. Technically, it still does have potential energy, right? Because we're talking about here gravity. When it's up in the air, it has a lot of gravitational potential energy. But when we're talking about chemistry, molecules and bonds and things, we also have another form of potential energy, the energy that's stored in a bond, right? So when you have one atom bonded to another one, they have a interaction between them, and how close they are is like how high we're lifting this respective to each other. And if you release those bonds, then you release that energy in a way, which is why sometimes chemical reactions get warm and sometimes they get cold. That has to do with potential energy in molecular bonds, not just in gravity, right? So potential energy doesn't just exist in the form of gravity, it exists, in other forms too. So technically, once it hits the ground, it doesn't have any more gravitational potential energy, but it's made up of atoms that are bonded to each other. So it has a lot of energy in that form. right? So that's when you have dynamite and stuff like that, right? There's a lot of potential energy stored in those bonds. If you do a chemical reaction to release that potential energy, boom, right? You get an explosion. And so everything in physics and chemistry is the movement of energy from one form to another. And so in chemistry, this is usually expressed as a quantity that we call heat. It's usually represented by the uppercase Q. Sometimes you see lowercase q as well. And why is it called the heat? Well, in chemistry, a lot of the time, this potential isn't going from gravity, so you have high, gravitational potential energy, to kinetic energy. It's going from the potential energy of chemical bonds into temperature, which is how fast molecules are moving. Right? So in chemistry, go from chemical potential energy to temperature. And we take advantage of this fact that, a law of thermodynamics is energy cannot be created or destroyed. It just moves from one form to another. We take advantage of this fact to then allow us to measure certain things that molecules do, right? We can't directly observe molecules, but we can measure how energy moves in a system, and that can tell us, for example, something like how much calorie do you have in your sandwich, right? If we can measure how energy flows, how much calories do we have in all the molecules in your sandwich is something that we can measure. Right? And so heat is just in chemistry, usually how we express energy, and it's going from chemical potential energy, energy stored in chemical bonds, usually in exchange with temperature. Either you get hotter or you get colder. And that temperature is going to be related to how fast molecules are moving. And so heat is measured in the SI unit of a joule, or a common unit of a calorie, right? So now we have a physical interpretation of what a calorie is when we're eating something. Well, it's just the amount of energy that's in whatever it is that we're eating. So an SI unit of a joule is equal to a kilogram meter squared per second squared. And then we can convert between calories and joules, which is another form of energy. Generally, with food, a calorie and a uppercase calorie, so this is kind of confusing, are different. Right? Usually food is measured in an uppercase calorie, and an uppercase calorie is equal to a K calorie. So that's what we would say is a kilocalorie, which means that is how many calories. Yeah, so one uppercase calorie is equal to 1,000 calories. So these are the common units of energy that we'll see. Joules, which is kind of the most broad unit of energy across all the natural sciences, and calorie is usually very specific to chemistry and other food sciences. Okay, so those are units. And so everything that we do with unit conversions, we can think about, and also when we're doing calculations with energy, right? If we're going between two different unit systems, calories and joules, then we have to be aware of our conversions between how we go between those dimensions, right? So there's going to be a specific conversion factor for joules to calories and vice versa. All right, so the last thing that I'll leave you with is when we think about heat and temperature, right? So those words are used interchangeably a lot. Heat is the total energy of all particles of matter, of whatever substance it is you're looking at, which means all the potential and all the kinetic energy, right? You add all of those energies together, and that gives you the heat of the substance. Temperature is related to the average kinetic energy of the particle, of all the matter, right? So if you have all of them, they're all moving at slightly different speeds or velocities, then the temperature is represented by the average of adding up all those velocities together, right? So temperature is gonna be related to how fast things are moving, and heat is related to all of the energy, all of the potential and the kinetic energy. So this is the potential energy plus the kinetic energy. And this is just, and sometimes this is used, these little brackets right here mean average, right? So you add up all the velocities, divide it by the number of particles, that gives you the average velocity. And so they're gonna be intimately related to each other, but they're not the same thing. Heat is a unit of energy, temperature is a unit, we use units of temperature for that, but that's a representation of the average kinetic energy. All right, so we can stop there for today.